Great. So today's topic is about benchmarking distributed SQL databases. And specifically, we compared Amazon Aurora's PostgreSQL API, YugaByte DB's YSQL API, and CockroachDB, these three databases that are PostgreSQL compatible. A quick intro, I am Karthik Ranganathan. I'm one of the co-founders and the CTO, as Jimmy said, and let's just jump right in. So just a quick intro to the distributed SQL space, right, before we jump in. The first question is, what is the fastest growing service in AWS? Well, it happens to be a database, and it's Amazon Aurora, and it's just absolutely been on fire, right? So this is the fastest growing database service in the history of AWS across all the services they launch. What is the database that powers Google AdWords and Google Play? And these are very critical services for Google that require very high throughput and as well as high consistency. Well, it happens to be Google's flagship database, which is Google Spanner, and that supports tens of millions of queries per second, right? And running some of their most critical services. So both of these qualify as distributed SQL databases. They distribute data, they're fault tolerant, so on and so forth. But they represent very different architectures, right? So in a nutshell, Amazon Aurora, its core selling point is it's a very highly available RDBMS, and it's fully wire compatible with MySQL and Postgres. And the same line for Google Spanner is it is the first horizontally scalable and strongly consistent RDBMS, right? So we're going to just quickly look at the differences and similarities between these two in an architectural manner, and then jump into what we're benchmarking and so on and so forth. Okay, so if you look at the architecture of these two databases put right next to one another, right, you'll find that Amazon Aurora is architecturally not built for write scalability. It has a single node that takes writes if you care about consistency, whereas Google Spanner can scale writes as you add more nodes, right? The second piece is fault tolerance and high availability, and both these databases are built with HA in mind. If you go towards globally consistent deployments, where you want your writes to be globally consistent, you typically cannot achieve that with Amazon Aurora because it does multi-master asynchronous replication, whereas with Google Spanner, it does strongly consistent replication, and so that is something you can achieve. If you're trying to scale your reads by adding more nodes, but you want each of your reads to be consistent, once again, Amazon Aurora cannot handle that because there is a single node that is the source of truth and everybody else is a slave that can serve stale data. Whereas with Google Spanner, it actually shards your table into smaller subsets of data and spreads them across the different nodes, so it can handle that. But where Google Spanner gives up against Amazon Aurora is the supremely important SQL feature set. Aurora has all RDBMS features, Postgres and MySQL, whereas Google Spanner is its own variant of SQL, and it misses like a lot of features, like even some basic ones, like for example, foreign keys and some types of constraints and so on and so forth. So with that in mind, what becomes interesting is if you can combine the best parts of Google Spanner and Aurora to build a database. And that has given life to a couple of open source databases, YugaByte DB being one of them and CockroachDB being another. And they're both Postgres API compatible. And it so happens that YugaByte DB is 100% open source. We just recently moved all our enterprise features to the open source as well. And the idea being that Postgres is open source and YugaByte DB is building a Postgres for the cloud, right? CockroachDB supports a smaller subset of Postgres features as compared to YugaByte DB. YugaByte reuses the Postgres code base, whereas Cockroach rewrites it in a different language. And it is not open source as of June 2019. So running production workloads with the database, you'd have to really look at the license and see if that works for you. Anyways, that aside, the topic is not licenses. So let's jump right into the topic. It's about benchmarking. And so the benchmark client driver is a Postgres SQL compatible client, right? So it speaks Postgres. So naturally, we picked Postgres SQL compatible distributed SQL databases in order to do the benchmark against. And these were the three that were fully Postgres SQL compatible: Amazon Aurora Postgres SQL, YugaByte DB, and CockroachDB. And they're all fairly the most recent versions that were picked. So that's exactly what you would use if you go use it at this point. If you now look at the Postgres compatible distributed SQL databases that we picked and what are the trade-offs between them, if you look at Postgres compatibility, YugaByte strives to achieve as high a compatibility by reusing Postgres, like I had mentioned before, including things like partial indexes, stored procedures, triggers, extensions, etc., as does Amazon Aurora, while CockroachDB gives up on a bunch of these features. On the horizontal write scalability side, Cockroach and YugaByte are very similar to Spanner, and they're horizontally write scalable, while Aurora is not. It has a single head node that takes all of the writes. And the rest of the features with respect to read scalability, like, of course, if you want consistent reads, then Aurora cannot offer you that. But if you simply want reads and you're okay with a little bit of stale data, then Aurora can absolutely scale really well by adding slaves. And fault tolerance is something all of these databases have, and that's kind of inherent to even be called a distributed SQL database, right? So with that in mind, let's jump to the benchmark setup, right? And why is this benchmark interesting and exciting? Like, firstly, it is an extremely simple benchmark. The idea was not to run something that is complicated like TPCC, which does a lot of things, because the trade-offs in different deployments in the cloud are quite different when it comes to simple operations itself. And that's because the network can get in the way of a lot of these operations. So let's look at what the benchmark does. So firstly, let's look at the workloads that we benchmarked, right? The first one is simply insert unique rows, right? So it inserts 50 million unique rows. Each row has a key and a value, a primary key column, which is key, and a value column, which is a value. 256 writer threads. We used prepare bind insert statements against all the three databases, and there were no reads against the databases when this workload was running. And the secondary index is also an insert workload. I mean, once again, we're focusing on the insert workload because we're trying to explore the scalability aspects of the databases. Like we did say, one of the major differences between the databases is that Aurora is not horizontally write scalable, whereas the other two are. And so like, we're just trying to get a feel for that, but it is important to get the numbers at a smaller scale as well. So the secondary index workload is also an insert only workload. It inserts the same key values, but in this case, the table has an index on the value. So it'll allow you to query by both the key and the value. Like you can do both type of queries efficiently. And we used 128 writer threads, and it's prepare bind and no reads once again. All of these were run in the AWS cloud in the Oregon region with a deployment, and the deployments are quite different between the way Aurora, like an Aurora-inspired database works and a Spanner-inspired database works. So we just made sure that whatever we did, it is multi-AZ, so it can tolerate a zone failure. So we did the best we could to kind of keep it at that design point, and then we used that to do a bunch of analysis. Now on the benchmark and the benchmark driver itself, the driver is open source. It's on GitHub. There's the link provided for you there. It's a Java-based app. It's quite a simple app, really, and it's something that you can reproduce for yourself. All right, so let's look at the Aurora PostgreSQL setup first. In Aurora, obviously, does not have multiple writers, so you cannot have like a synchronous replica across, like an active across, like even though this says async replication, at the disk level it is synchronously replicated, and the failover is async, so it's kind of a little different compared to how Google Spanner works. But nevertheless, the writes hit the writer node. The writer node is in the US West 2A zone, and it has 16 vCPUs. And the data gets written into, gets replicated at the disk level, which is below the database level. And there is a reader in one of a different zone that is a hot standby in some sense, but you would have to fail over to the reader in order for it to start taking writes. So it would have to get promoted to being a writer. The reader has 16 vCPUs, and it is in the US West 2C zone. So the same region, US West 2, but a different zone, right? And it shows you the Aurora screenshot and so on. Again, we'll talk about instance types in a bit, but we use the db.r5.4x large, which is the 16 vCPU, and there's really no choice in the type of an instance in Aurora because it's a managed service. Okay, the setup for YugaByte and CockroachDB are quite similar. They're both inspired by Google Spanner. So put 3 writers in 3 different zones. And there's no difference between a writer and a reader because the table is internally sharded and the data is kind of spread across these 3 nodes. So each node does reads and writes for a subset of the data. Each of the nodes is 16 vCPUs, and it's US West 2A, 2B, and 2C. So it's a three-zone deployment, and it gives you active-active semantics in the sense if one of them fails, the other one seamlessly picks up. So, and it's fully consistent, so you don't have to worry about failures in this case or promoting one to become a reader or a writer or so on and so forth. Okay, so folks might already have a lot of questions, but we're going to cover a lot of analysis on this, like how come this takes 3 nodes, the other one has 2 nodes. So we're going to look at all of these questions, but let's keep going. All right, so I think there's also a question that came up. I don't know if, okay, so we'll maybe look at it at the end. All right, so the first benchmark we did was the simple inserts benchmark against these 3 databases. On the left, the bar charts show you the write throughput. On the right, the bar charts show you the latency. The YSQL Postgres compatible API of YugaByte DB did 45,000 writes in the setup. Aurora did 28,000, and CockroachDB did close to 10,000. And the latencies were 4.5 milliseconds for YugaByte DB, 9 milliseconds for Aurora, and 35 milliseconds for CockroachDB. Now, okay. Can this be improved? YugaByte DB supports multiple APIs. So there's another API called YSQL, the YugaByte Cloud Query Language. It is a semi-relational API, and benchmarking the same type, it is not the same driver because it's not Postgres wire compatible. It is Cassandra Query Language wire compatible, but writing the same type of statements where you insert the rows into the table with no reads going on with exactly the same semantics in the benchmark setup, we see that it's able to do 85,000 inserts per second at 3.5 millisecond latency. And both YSQL and YSQL run on top of the same core distributed storage engine of YugaByte called DocDB. So what this shows is that we would actually be able to push up the performance that you observe with YSQL pretty close to what YSQL does, and that's a bunch of feature enhancements, and those are some of the things that are ongoing. Okay. The second workload is inserts with a single secondary index, like we had discussed, so key value and an index on the value. So that means every write has to insert to the primary table and to the index table. The YSQL Postgres compatible API was able to deliver 5.3 thousand inserts per second, with the index also included inside, of course. Amazon Aurora was able to do 20,000 inserts, and CockroachDB was able to do 3,500. And the latencies were 22 milliseconds, 6 milliseconds, and 73 milliseconds respectively, right? And again, what is the variance, what changed? We're going to look at some of this analysis, right? So these are just the raw results, and we talked about 2 things. We talked about the simple inserts and the inserts with a secondary index. Okay, so let's go into the analysis, right? So a lot of folks had pointed out or asked about what the isolation levels of the databases were, and if it was apples to apples, if we used one isolation level versus another. So let's dive into all of that stuff, right? So first off, the benchmark was done with default isolation levels across all these databases. And as isolation levels go, the lowest isolation level of the set put on the screen is read committed, which is the default for Amazon Aurora's PostgreSQL. In fact, it is the default for PostgreSQL itself. The default for YugaByte DB is snapshot, and the default for CockroachDB is serializable, right? So we use the defaults to get these numbers, and if a database is able to support consistency and ACID semantics for these inserts and these secondary indexes at their default isolation level, then as a user, there's probably no need to bump it up, was our reasoning. However, let's go through the whole analysis, right? Serializable is the strongest isolation level, snapshot is next, and read committed is the lowest. So a number of people said, like, this is kind of unfair because some databases are at a much higher isolation level compared to the others, and so they would have to do extra work. So it now brings up the question, is it fair to actually compare with different defaults? I mean, we redid the experiment with serializable for YugaByte anyways, but nevertheless, it is a philosophical point of view. It is what you're trying to achieve with your benchmark is really the bottom line. With traditional RDBMSs, RDBMSs actually go to extra lengths to support a lot of these primitives, like a secondary index or like your insert, et cetera, at weaker isolation levels, because for your system as a whole, it gives you much better performance. And from a user's perspective, they would think about the set of operations they want their application to do, and then choose the ACID consistency semantics for that app, and choose the isolation level based on whatever the best performance they can get from their database given the app, right? So in this case too, if you think like a user, if I have an application that does inserts and of a single row and inserts of rows into a table with one index, you would probably choose the isolation levels for the databases that give you the best performance, right? So that was the rationale behind doing this. However, let's take a deeper dive into the isolation levels across various databases. Like, suppose you had to look into the problem of, hey, I have a workload that does inserts and secondary index inserts, right? So these two type of workloads. Let's pick a bunch of databases that give you consistency. So there's Oracle, there's YugaByte, there's Aurora, and Cockroach, right? And let's put down the various isolation levels on the left. There's serializable, which is the strongest, and then there's snapshot, slightly weaker, and then read committed, which is the weakest of this group. Now, Oracle famously has an isolation level called serializable. However, it does not exhibit what the serializable isolation level actually describes. So it really just supports snapshot. And if you want to achieve serializable, you need to do something in your app to figure out what rows you need to lock, et cetera, to get serializable semantics, right? And Oracle does support read committed as well. And its default isolation level out of the box is read committed. And it does support operations such as secondary indexes at its default isolation level. YugaByte supports both serializable and snapshot. It does not use read committed. So if you ever make a query to YugaByte at the read committed isolation level, it automatically uses snapshot isolation in order to serve that. And its default is snapshot. In the Aurora's case, it supports all three. It supports serialized because it's PostgreSQL, and PostgreSQL supports serializable, snapshot, and read committed, with the default isolation level being read committed, and it does support secondary indexes with consistency guarantees at that isolation level. CockroachDB supports, from what I understand, only serializable as the isolation level. So if you go for any weaker semantics, you pretty much get up converted into the serializable isolation level. And that's the default as well, right? So what we had done was we had picked, obviously, the defaults that would serve the purpose, which is, I guess, in the speak of the database vendor, what is the isolation level at which you get the best performance for the given workload? So Cockroach, there's really no choice but to choose serializable. With YugaByte, we picked, with Aurora, we picked read committed, which is like the lowest level, which gives you the best performance. And with YugaByte, we picked snapshot, which is its lowest level that gives you the best performance. However, many people pointed out that given the similarity in the architecture of YugaByte and Cockroach, it would be important and interesting to repeat what the performance of YugaByte is at serializable. So we ended up doing that as well. And these results were not presented before, but that's something we'll look at right over in this section, right? So here's another bar. So there is a blue bar, and it happens to be the performance of the latency of YugaByte at the serializable isolation. So the throughput is exactly the same, 45,000 operations per second, and the latency is slightly higher, like 5.6 milliseconds. I mean, the experiment was obviously, like, there's a little bit of variance in the cloud anyway, so how much of that is down to that and how much of it is something that we can improve is something we can talk about. But anyways, that was for the simple inserts. This result is for the secondary index, where the throughput is, again, exactly the same. Like, I mean, like maybe the last two digits were slightly different, but effectively it's the same throughput. And once again, the latency was slightly higher, right? So is this surprising? Like, did we expect this? Yes, for YugaByte, we don't expect any substantial difference in its performance at serializable versus snapshot for these two workloads. The reason is because both, like, if you take a simple insert and if you take a secondary index, right? A secondary index is a distributed transaction inside YugaByte. A simple insert is a single row transaction inside YugaByte, right? So it's really optimized for single row transactions. However, for any operation happening in YugaByte, if the set of keys the operation reads, which is called the read set, is exactly the same as the set of keys it writes, then there's really no difference between the way serializable and snapshot works. It is possible for us to, in certain cases, improve the performance at snapshot when, like, even for the same workloads, but currently it is just following the same path. If you take a single row insert has to check if the row is present or not, which means it kind of has to read the existing row, and then it has to write it if it is not present. So the read set and the write set are the same. Similarly, for the secondary index, it has to go read the original value, like the key to value, and then it has to delete the existing value. But in this case, we were doing simple inserts, so there'd be no delete. It reads the original value to see if the row was present. The row would not be present. It inserts the key to value row in the primary table, and it inserts the value to key row in the secondary table. It also should check if the value to key had a different mapping in the secondary table, which it does not. So, but however, the read set and the write set is exactly the same in this operation. So because it's the same for these two, we don't really see a difference, and that's quite expected. Okay, so after the second piece of analysis, right? And this is something that's a little harder to understand from the perspective of two completely different architectures. So these architectures are not symmetric, right? Like Amazon Aurora PostgreSQL has two nodes, one taking all the writes and the other not, and the other two have three nodes, each with 16 cores. So it's possible to readily point out, like, hey, there's the total number of cores is different, the total number of nodes is different, and we can get into a lot of that, right? So this section addresses how do we make these benchmarks comparable, right? So, and what is a fair comparison? So in the case of Aurora, here's the setup. There's two nodes, one writer, because you cannot have more than one writer. All the writes hit your writer node. We're able to do 28,000 writes per second. This is a simple inserts workload. And the replication happens underneath, but the reader is sitting idle. However, if you don't have the reader, you don't have multi-zone availability, right? And if you take the two in combination, it is 32 vCPUs in order to make sure you have a fast failover to a second zone. If you take CockroachDB and YugaByte it's like 45,000 writes for YugaByte or close to 10,000 writes for CockroachDB, but it is across three zones. The writes get sent to any node, but then it gets relayed to the appropriate node, and each node is able to handle a subset of the total number of writes. And the effective aggregate number of vCPUs across this setup is 48 vCPUs. So if you were to look at this again, in the Aurora case, all of the writes are handled by 16 vCPUs, but you need 32 for multi-zone availability. For the other two, you have 48 vCPUs handling all the writes, and they are a multi-zone available system as is. So how can we compare these two objectively, right? So here's a couple of thoughts at this size that the comparison can be done in an objective manner. However, like, note that there's two parts to this. There's one part about how to compare it at this performance point, and there's also another part about what happens if you scale, right? So these numbers become instrumental for both aspects of the discussion, but let's just focus on, at these numbers, how can we compare these objectively? Well, the first way is to normalize the total number of IOPS you get per vCPU, right? So if you take YugaByte, it does 45,000 writes, but it takes 48 cores to deliver that. So you divide those two numbers, you get 937 IOPS per vCPU. I mean, if you do the same calculation for Amazon Aurora, you come up with 875. And if you do the same thing for CockroachDB, you come up with 204. Now, if you don't have that second node in Amazon Aurora and make it 16 vCPUs, obviously your IOPS per vCPU will double, but you no longer have multi-zone high availability, right? So these are trade-offs, again, depending on how you want to deploy, but that's the purpose of a benchmark, is to make you think about trade-offs and give you a framework to kind of work through those, right? So that's that. Your second method, and this is the one that, you know, people trying to run larger services typically prefer, is what is your dollar per IOPS, or dollar per 1,000 IOPS in this case. YugaByte is doing 45,000 writes with 3 instances. Those instances are of type i3 4x large. That's the one we benchmarked. The monthly cost is $2,740.62. right? And that's just the Amazon IaaS cost. And we're not doing things like reserved instances, et cetera, which drop the cost even further. And it's fully open source, so you have all the enterprise edition available to you. So you should be able to run it with that expense, right? And so that's going to be $61 for every 1,000 IOPS per month. And if you start doing, like, if you drop down to a C5 4x large, you'll be able to drop the price instead of an i3, which has NVMe drives. If you do reserved instances, you can drop it more. So you can do a bunch of tricks there. On the Amazon Aurora side, there's 2 nodes of DB-R5 4x large. Obviously, it is a managed service, so the price is quoted with the managed service in mind. And we're just putting the same storage that is available to you with the i3 4XL nodes. So it's just the equivalent storage, and that comes to $141 per 1,000 IOPS per month, right? So, and here, once again, you could reserve instances and drop the price, but you don't have the choice to change machine type. That's kind of baked into the service. This analysis is kind of tough to do for Cockroach because it's not clear, since it's not open source, if you can just run this as is, what are the other costs that come in. But you could imagine if you have those numbers, you could do a similar analysis to figure that number out. Okay, so let's keep going. Like we talked about how to compare these two architectures in a couple of methods, and these methods really depend on what you're trying to achieve and your scale and a number of things, right? So talking about scale, let's look at, so these numbers are true at the smaller end. Like if you just have like, a few thousand writes per second that you want to do, then these numbers are accurate. But I'm just going to go on a hunch and say, given the brand power of Amazon and given the power of default of Aurora, you're probably going to just pick Aurora, and you're not probably going to look at any of the other databases because it's so much simpler, so much easier, and so much safer, right? Every which way. So that brings us to the more important topic of why even build these databases, right? So what happens if you want to scale your writes? Your app is growing, your microservices are growing, there's more users interacting, there's more data coming in, and you need to scale, right? What you would find is that, like, let's walk through the logic here. We picked a DB-R5 4x large, which is a 16 vCPU machine, and for our workload, we saw 28,000 writes per second, right, on Amazon Aurora. Now, since only a single node can take writes, you could go up to a DB-R5 24x large, which is 6 times bigger, and has 96 vCPUs, but that is absolutely the largest node you can get for Amazon Aurora. So assuming that the database in the software is able to scale with more vCPUs, 28K into 6, 168K is your maximum, right? So that's all you can do with an Amazon Aurora if you want consistent writes for the simple inserts workload. Now, obviously, this is going to get spread across a number of your tables and et cetera, et cetera. But if your write load is growing, that's all you can do with a single node of Aurora. And after that, you have to figure out strategies on how your app is going to write across 2 different nodes. And at which point you've kind of given up on the distributed SQL semantics, and you'll have to figure out app sharding and no transactions across these nodes, no indexes across these nodes, so on and so forth, which is a very complicated endeavor. Okay, now with YugaByte, we put it through the ringer and we said, like, okay, if we claim we're like horizontally scalable, what can we do? And we were able to achieve over 1 million inserts per second with YugaByte because we were simply able to keep adding nodes. And the graph shows you what we observed when we took the screenshot. And it's just to show that it's not run for like a couple of seconds. It was running for an extended period of time, and it's able to keep up. We were able to do about 1.25 million inserts per second. And the server-side latency was 1.66 milliseconds. And this was on a 100-node cluster, each of 16 cores. It was the C5 4x large. So we just opted for the cheaper variety of hardware to show that this is possible to achieve even with a cheaper set of nodes. So this is how it looks in comparison. So a write scalable database like YugaByte is able to grow linearly in the number of writes, whereas you have a max cap in Aurora PostgreSQL, right? So this answers the reason as to why these databases are even being built, given that there is a dominant database like Aurora in something like Amazon. Okay, so let's go to the last piece of the analysis. And if you folks had followed carefully, you would have noticed that the latency versus scalability numbers between SQL and Aurora are quite different, right? And actually across all of these, the only thing that stands out on this page is that Aurora is able to do a lot more throughput at a lot lower latency. The question is why, right? So effectively, you're getting almost a 4x better throughput and about a one-fourth the latency, right? Like, and so it's interesting to try to explain the why of this, right? So I'm going to talk about YugaByte here. As you noticed, most of the in-depth discussions I stick to YugaByte because that's the database I know. I don't know enough about the internals of Aurora or Cockroach to go into the internals, but the empirical observations, more than happy to share. So the latency for YugaByte is high and the throughput is lower because every operation in a secondary index insert workload is really 4 operations that are multi-node RPCs inside the database, right? Firstly, we created a replicated entry, so 3-way replicated entry in a table called the transaction status table, where we say that this is a multi-node transaction in progress, and then we write a provisional record for the row. We write a provisional record for the index, and we have to make it provisional because these two cannot be visible. They have to be atomically visible, the row entry and the index entry. And finally, we flip both to make it visible by marking the transaction committed. So there are 4 different operations that are going inside. Whereas in Amazon Aurora PostgreSQL, all the operations are local to the writer node, and it simply replicates the data at the disk level below. So the upshot of this is that you would expect a fourth of the like the throughput because it's doing 4 times more RPCs, and you would expect 4x the latency because internally it's kind of doing 4x the work, right? And some of these are across zone and like the number of boundaries it crosses and so on and so forth. So if you now take scalability, right? However, it is true that you do get much better performance at whatever the benchmark point was. But if you take scalability into account, you find that once again, it does about 20,000 writes per second for our number of cores, the 16 core nodes. If you go to 96 cores, it'll give you 6x more. That's 120,000 writes or inserts per second into a table with a secondary index, or more generally, transactions, right? It'll give you 120,000 transactions per second. And it's capped at that. Like after that, you have to figure out how to split your data across nodes and so on and so forth. Whereas with YugaByte, you should just continue to be able to add nodes and perform these transactions because every transaction only involves a fixed set of nodes, right? So there's like in the worst case, there are 3 nodes that hold the transaction status tables row. There's 3 nodes that hold the primary data row and 3 nodes that hold the indexes row. So there's no more than 9 nodes that participate that could participate in a distributed transaction. And we try to optimize these 9 nodes to just like 6 nodes by picking, by intelligently placing data. So irrespective of how many nodes you have in the cluster, it's only 6 nodes that even can participate in a transaction. So what is the upshot of the analysis we have done? Like Amazon Aurora PostgreSQL has better throughput and lower latency if you don't care about write scalability. So that actually makes it a great database to pick for that design point. However, if scale out is important, if you care about horizontal write scalability and if you don't want to get capped at some point, then a scale out SQL database like YugaByte is a better choice. So that's all I had. That brings us to the end of the presentation. Like we'll open it up for questions, but before that, I want to just say, we're 100% open source. Our community is growing really fast. We'd love it if you folks joined our community if interested, like yugabyte.com/Slack. We also love GitHub stars, so please show us your support, like stars on GitHub, and do download and try it for yourself by going to our download page, which is actually a newly designed download page.